This is the solution to problem number 15 from section 8.5. This series looks a little weird because the terms in our series are themselves a sum of two things, and we haven't seen too many problems like that. It's not wrong if you want to try to combine these into one expression, but I'm a little skeptical because these are two different types of things. This is an exponential function of k, and this is just based on powers of k. So even if we get a common denominator and combine them, we're not going to have a lot of hope to simplify that expression. So I'm not sure how much that helps, but that would be one way to try. What I'm going to suggest is that we play around with this first to get a sense for what's happening by looking at the two series separately. In other words, look at this sum and also look at this sum and see what they're doing individually. One rationale for doing that is that if they were to both converge, then we do have a theorem that says that the series from the sum of these two sequences is just this guy plus this guy if all those things converge. So if this series and this series converge, then the original series will just be the limit of this one plus the limit of this one. So that is one of the series manipulation rules that we have. But it does assume that both of those things have a finite answer, and I don't know that. So I'm not going to just break it apart and assume that. I want to check each one separately. But that at least is a reason to at least consider what they look like separately. So let me start on the right. This guy over here, this is a geometric series. And this geometric series has a ratio of 7 to the minus 1. If that's not obvious to you, you might want to start the problem by writing out several terms of this. So, for example, when k is 1, we'd have this. When k is 2, we'd have this. When k is 3, and so on. And so you can see that this first term, the second term, 7 to the minus 1, 7 to the minus 2, 7 to the minus 3, and so on, that's what this guy is. So this is just pulling out each of those things separately. And if we were to write those down, then we can see why it looks like a geometric series. They're just powers of 7 to the minus 1. So that's 7 to the minus 1 to the first, plus 7 to the minus 1 to the second, and so on. So the thing on the right is a geometric series with a ratio 7 to the minus 1. 7 to the minus 1 is 1/7. That's smaller than 1, so this is convergent. And if it helps to know, we actually know what that sums to, because we know the common ratio is 7 to the minus 1, and the first term is 7 to the minus 1. So remember, our geometric series formula for convergent geometric series is based on the first term and the common ratio. So we 100% know what's happening with the right-hand side, this sigma on the right. On the left, we're not quite so fortunate. We can factor a 7 out, and then this should look at least a little bit familiar. This is the harmonic series, which is also known as the P series with P equal 1. So the way that we test for convergence of P-series is with the integral test, but once we've done that, we can just remember the results. P-series converge only if the P, the power of k that we're using, is bigger than 1. Any other value of P would have a divergent series. In this case, P is equal to 1, which is not bigger than 1. And so, therefore, the series on the left diverges. So now at least we have some idea of what's happening here. We have a value that its contribution in this sum is infinity, and then we're adding on to that a little bit more. So the fact that the harmonic series goes to infinity and we're adding on a little bit to it means that we seriously believe, or I seriously believe, that this original series diverges. But how do I make that official with one of my tests? How do I verify that with one of my tests? Well, that's actually not too hard now that we see what's going on. We know that we have the sense that this diverges, and we have the sense that the culprit is this part. So I can now turn this into an instance of the comparison test. I know that this expression will always be greater than just this part. So the thing that I'm summing for real is bigger than just this expression, the 7 to the k. So that means that summing up all of these expressions like I have in the problem is going to be a bigger value than summing up the corresponding values of 7 to the k, 7 over k. What we just showed over here on the left is that 7 over k is tending to infinity. And so by the comparison test, I have shown that the series that I'm interested in is bigger than, I should say greater than or equal to here. The series that I'm interested in here is greater than or equal to this series, but this series goes to infinity. So the conclusion is, therefore, this guy goes to infinity. So that stuff at the bottom, that is straight up comparison test. So by comparing this series to this series, I'm 100% sure that the one that I am interested in, the sum of these a sub k's, is greater than or equal to the sum of these b over k's, or b sub k's, and I know that this is divergent. So therefore, this one is divergent.